Alright, as mentioned earlier, the multi-phase reactors, the difference with single-phase reactors that multi-phase reactors have mass transfer steps, which comes together with the reaction steps. So frequently in big reactors, the mass transfer steps will actually control the overall reaction rate, usually. And every mass and energy balance, it has to be written and solved for each species in each phase. And gravity is an important element that control the patterns of the phase. So the lighter phase will be rise and denser one will of course fall. There is mixing within phases, and also there is mixing between phases, and this mixing effect has it's dominant in multi-phase reactors. And solubility and phase distributions of species between phases require careful application principles. So this is an example. Let's say you have a multiple phase reactor here, and let's say this is phase alpha, and this one is phase beta. So it can be alpha is gas, beta is liquid, or the other way around, beta is gas or alpha is liquid. This is just to show the theory to separate the phases, for example. But I guess, of course, the alpha is, of course, the gas because it is lighter, and beta, this one is, of course, is liquid because it's denser. And the dash dot here, we called it as permeable area. Permeable area between phase alpha and beta, between phase gas and liquid, for example. So we call it as interfacial area between gas and also liquid. Then theoretically there is concentration of species J initially, and when it's out, this is the unreacted species J. So at beta phase we have volume at beta phase and also residence time. So the same thing over here. So we put it as superscript because in this book it shows as superscript. It doesn't mean the exponential. Okay. So to further and to enhance your understanding on mass balance, you need to have a look or revise the mass balance equations for single phase reactors. So you can have a look at your previous what you call that, previous lecture or previous code that teach you the mass balance equations, CHE502. And also for multiphase reactors, you can refer to Smith books. All right. Okay, let's have a look at mass balance. The mass balance theory for alpha phase and if it is unmixed. So the theory is velocity at alpha phase times differentiation concentration of species J at alpha phase divided by differentiation of length of that reactor equals to summation of volumetric of species Ij and reaction of I, for example, where I is maybe the limiting reactant, plus gain or loss to other phases. This if it is unmixed. So if it is mixed and it is at transient means there is mixing between two phases. So you have to use the volume at alpha phase times differentiation of concentration at alpha divided by differentiation of height of the reactor equals to the volumetric at alpha phase times the subtraction of concentration of J unreacted at alpha minus concentration of J initial at alpha phase plus volume at alpha phase times summation of this one, volumetric times reaction rate, plus gain or loss to other phases. So if it is mixed fluid, but it is at steady state, so you have to regard this area to be 0. So to calculate tau at alpha phase, it's simply as a volume of fluid or reactor at alpha phase, actually volume of fluid, okay, divide by volumetric at alpha, and tau at beta, so volume of fluid of beta divided by volumetric at beta. Especially for a plug flow reactor, for example. So this is the theory. Instead of you use the volume over divided by volumetric, maybe you can use this the length divided by average velocity. So this slide is introducing you the flow configuration of phases. It can be mixed, and mixed means that if this is reactor, there has two phases here, and maybe there is mixing at alpha phase and beta phase. And there could be a configuration where there is no mix at beta, but mixing at alpha. And then there is no mixing at alpha or beta, but the flow is co-current. And there is no mixing at beta, at alpha and beta, but the flow is countercurrent. Okay, this is flow and this flow. Okay, if the reaction is happen only at one phase, for example, maybe the reaction only happens on solid phase, which is catalyst, right? So what are the functions of other phases? So basically other phases, the role is to supply reactant or to remove product and to provide catalyst medium as a catalyst for catalyst to positioned. Example, in moving bed or slurry or fluidize, the reaction happens only on catalyst phase. So you can see that there is gases going out and liquid. Gases keep going in and going out, liquid, the stagnant position of the liquid. So there you can see that the other phase to as the supply reactant and also to remove product. And the catalyst phase in these types of reactor is continuously added and removed. Okay, so let's have a look at interfacial surface area. So interfacial surface area, just now the previous slide introduced as permeable area. Okay, permeable area. So let's say A for area, and phase alpha and beta. So this is interfacial surface area. So what does it mean? It is actually the breakups of liquids, so that or the breakups of the air. So liquids to be drops and air could be into bubbles. And the interfacial area can change. The area can change, depends on the conversion, geometry, and also flow conditions. So the stirring with an impeller or the flow pattern caused by gravity can control the interfacial area. So the design and position of impeller actually provides effects on the efficiency of breakups of liquids into drops and bubbles, and therefore it could increase the interfacial area. So the interfacial area has this surface tension, and it is a very important element to determine drop and bubble size and shapes. The other factors is the presence of surface active agents that can alter the interfacial tension between phases, which it has big effects on surface tensions in multiphase reactors. So as illustrated in this slide, look at here. If the impeller or this the propeller here, if position is like this, so you can see that the flow will be like this, and if they it will be a big flow, for example, so it can break up the interfacial area between gas that's going in with liquid. But if the impeller position to be like this, it could be the drops is lesser, the interfacial area could be lesser. So here, suitable design and positioning of impeller can provide efficient breakups of liquids into drops and bubbles. And also the flow pattern that caused by gravity also can controls the interfacial area. And see, the interfacial area is so bubbly, and this one is quite slug, and this one is churn interfacial area, this one is annular, this one is dispersed. So these are some of the examples of the interfacial area. This is the example different design of impeller. So this one is anchor, this one is propeller, 6 flat blade disc turbine, pedal, gate anchor, and helical screw. So all of these are stirrer that is being used in multi-phase reactors in industry. Why we need that? Because the reactors is so big and it provides better collision between phases, and so that it will increase the interfacial area, so that the reactions would increase as well.